This is lesson 1.2, Inequalities and Solutions to Equations. We have two objectives. First, you should be able to identify and use inequalities. We got a new vocabulary word. And then our second objective is talking about when we solve an equation. You should be able to tell when that equation has one solution, infinite solutions, or no solutions. All right, so go ahead and write these down. When we talk about inequalities, there's four different kinds. We could have less than, we could have greater than, or we could have less than or equal to, or greater than or equal to. The or equal to is denoted with just the line underneath. All right, so I did the first one for you. 45 is definitely a larger number than 23, so we put greater than in there. 45 is greater than 23. Go ahead and do the remaining 5 on your own. Example 2, and then all the practice problems. All right. 79 is greater than 75. 57 is greater than 13. 42 is greater than 35. 60 is greater than 50. And 320 is greater than 316. Not sure why I set it up this way. Maybe I was just feeling like greater than. But anyways, you should know how to graph inequalities. So when we're graphing an inequality, I'll go over the red and blue stuff here in a moment. But let's just say we're trying to graph this inequality here. X is greater than or equal to 9. The first thing we're going to do is draw a number line like we have below, and we're going to draw some tick marks. Right in the middle of the number line, let's put that number we're comparing X to, and then we should put a few numbers to the right and a few numbers to the left. To the right of our number 9, we can count by ones, 10, 11, 12, and then to the left, 1 less than 9 is 8, and then 7, and then 6. Okay, so we can draw our solution to this inequality now. We're comparing X to the number 9, so we're going to put a point on the number 9. Now this circle, this point, could be open or it could be closed, depending on whether or not we have an or equal to line under it. So if it's strictly less than or strictly greater than, then the solution does not include the endpoint. We leave it open. In this case, we have an or equal to line. So it's like this, where we close the circle to show that we're including the endpoint. 9 is a solution, because if I replace X with 9, we get a true statement. 9 is greater than or equal to 9, because 9 is equal to 9. But 9 is not the only solution. So let's check. It's either all the numbers to the left of 9 or all the numbers to the right of 9. Let's try 8. 8 is one of the numbers to the left of 9. If I put an 8 here for X, do we get a true statement? Is 8 less than or equal to 9? I'm sorry, this is a greater than sign. Is 8 greater than 9? No. So these numbers to the left of 9 are not solutions to this inequality. However, 10 would work, right? Because if I put 10 here for X, 10 is greater than or equal to 9, and so is 11, and so is 12, and all the numbers bigger than 9 are solutions. So to show that, 9 is a solution, and all the numbers greater than 9 are a solution. So we draw an arrow to the right to show all the numbers bigger than 9. All right, let's try example number 4. This time we have -3 is less than t. I went ahead and did this one already. I did want to show you, you can draw your solution arrow. You can draw it on the number line like we did in the last example, or you can draw it just slightly above the number line. Either way is fine. However, notice that this is strictly less than, so our circle is open, just like here. Now some people take a look at this and they say, wait a minute, that's a less than symbol, so how come we're not shading to the left? And I want to point out that it doesn't say t is less than, it says -3 is less than our variable. So I recommend picking test points, like try -2 or -1, or the next number would be 0, right? Could I put in a 0 here? Is negative 3 less than 0? Yes, it is, because that's a negative number and 0 is not. If you tried it the other way, like put in a negative 4 or a negative 5, you would get a false statement. Negative 3 is not really less than negative 4, so that's how we know not to shade to the left. If you don't like thinking of it that way, picking test points, you can always rewrite it with the variable on the left-hand side. And then we have t is greater than negative 3. If you prefer to think of it as greater than shades to the right, that's only true as long as you have your variable on the left-hand side of your inequality. Okay, try these two practice problems on your own, and then come back and check your work. Practice problem 5, that's a strictly less than, so we should have an open circle. And we're shading to the left because all these numbers are less than negative 4. In practice problem number 6, we should get something like this. If you want to, switch the order around, make sure the alligator is still eating the 6. P is less than or equal to 6, so we're shading all the numbers less than 6, and we fill in the dot because it could be equal to 6. All right. Before next thing we're going to do is solve inequalities where the variable's not yet by itself. And I want to preface this with when we were solving equations in the last lesson, I told you to just keep the equation balanced, do the same thing to both sides. We can do that usually, but not all the time. So let's find out what the special case is where we can't just do the same thing to both sides. Let's do this activity together. I hope you all would agree with me that this inequality is true. Negative 2 is definitely less than 5. Negative 2 is a negative number. 5 is positive, so negative 2's got to be less than 5, right? Let's check addition. Can we add the same thing to both sides and still get a true statement? Pick any number you want. I'd like you to really do that. Pick a number, and please pick a different number than me in your notebook. I'm going to take an easy one. So when I check your notes, nobody should have the number 1. Pick any other number you want. Now, add your number. I'm going to do 1. You try a different number to both sides of the inequality here. So I'm going to have negative 2 was on the left side of the inequality, and I'm going to add 1. And then on the right side of the inequality, I had a 5. Again, I'm going to keep my inequality balance. We'll see if this is a valid thing to do. I'm going to add 1. And when I combine my like terms on the left side, negative 2 plus 1 is negative 1. Is that still true? Is it still less than 5 plus 1 is 6? Is this true? Yes, it is. It's true. And it turns out, this is not a proof, but no matter what number you picked here, you would still get a true statement. Yes, so we are allowed to add the same number to both sides of an inequality. Can we subtract? Let's use the same number. So again, I used 1, you use your number, but subtract it from both sides of the inequality. So our inequality was negative 2 is less than 5. I'm going to subtract 1 from both sides. Is this true? Well, negative 2 minus 1 is negative 3. And 5 minus 1 is 4. Is this true? Yeah. We've got a negative is less than a positive, right? That's true. Yep. So we can subtract the same number from both sides of an inequality. That's also allowed. What if we multiply by a positive number? Please pick a positive number here. Again, I'm going to pick, don't pick 1. I'm not going to pick 1 either. I'm going to pick 2. Oops. Let's do that in blue. Multiply both sides of our inequality by a positive number. So our inequality was negative 2 is less than 5. I'm going to multiply both sides of the inequality by my number I picked. You should multiply by your number you picked. 2 times negative 2 is negative 4. Oh, I should put a question mark here. We're asking, is this still true? So is negative 4 still less than 2 times 5? Is that still less than 10? Yes, it's true. So we can also multiply both sides of an inequality by a positive number. Can we do it with a negative number? Let's try. Pick a negative number, any negative number you want. I'm going to steal the easy one. I'm going to pick negative 1. Pick a different negative number. Multiply both sides of our inequality by negative 1. So I'm going to take the inequality. Negative 2 is less than 5. And I'm asking, if I multiply both sides by negative 1, do I get a true statement? Well, on the left side, negative 1 times negative 2, hopefully you remember that a negative times a negative is a positive. And then negative 1 times 5 is negative 5. Is this true? Is 2 less than negative 5? No, it's not. So again, this is not a proof, but it turns out that we can add any number we want. You might have picked a negative number here. It would still be true. You can add that number to both sides of your inequality. You can subtract that number from both sides of your inequality and still get a true statement. You can even multiply both sides of a true inequality by any positive number you want. I chose 2, might be something else. But when you multiply by a negative number on both sides of a true inequality, you will always get something that's false. And what will end up happening is, since this is always going to be false, this inequality is always facing the wrong direction when you multiply both sides of that inequality by a negative. So it's an easy fix. This is our result. This is really important. Write this in a note card when we take our test. If we multiply or divide both sides of an inequality by a negative number, then the direction of the inequality must change. If you keep that rule in mind, then you can really just do the same thing to both sides of the inequality, just like you would with an equal sign, as long as you apply this rule when you're multiplying or dividing by a negative. So let's try it together. Here's example 5. I am going to, well, actually first, remember in our last video, what's happening to the variable? Negative 5x means negative 5 times x. I'm multiplying x by a negative 5. So if this were an equal sign, I would divide both sides by negative 5. But remember our rule on the last page, I'm dividing both sides by a negative number. So I'm going to rewrite the left side of my inequality, rewrite the right side of my inequality, but I'm not going to draw the greater than symbol. I'm going to divide both sides by negative 5. And because I'm dividing by a negative, the direction of my inequality has to change. So that greater than symbol becomes a less than symbol. And then I simplify. So negative 5 divided by negative 5, that's just a big fat 1. 1 times x is just x. And now I have a less than symbol. 10 divided by negative 5, a positive divided by negative is negative. So I have negative 2. Let's try example 6. This is a two-step problem because we have our variable being multiplied by a number, and then we have some subtraction. So again, we're undoing it. We're going to do the order of operations in reverse to get the variable by itself. Let's go ahead and we'll take our inequality, and we're going to add 7 to both sides. That's allowed. You can add any number you want to both sides of an inequality, and that less than will stay a less than. When we combine our like terms, 3 plus 7 is 10. Negative 5n, and then negative 7 plus 7 is 0, so I'm not going to write anything. Now, I can divide both sides by negative 5 to get n by itself. But because I divided by a negative, the direction of my inequality has to change. So that less than became a greater than. Simplifying, we get 10 divided by negative 5 is negative 2. And now we have n by itself. You can write it this way, or that's the same as saying n is less than negative 2. Either one is fine. Try practice problems 7 and 8 on your own, and then come back and check your work. Okay, so remember we took this negative 6 and distributed to get these terms. Then we're going to combine our like terms to get the next line. Add 39 to both sides. Now we have the term with x in it by itself. All we have left to do is divide both sides by the coefficient, the negative 24. And since we're dividing by a negative, the greater than or equal to sign switches directions. And so we'll get a final answer of x is less than or equal to 3. Let's practice problem 8. Again, distribute first. After that, we can undo this addition here by subtracting 42 from both sides. Combine your like terms there. And then again, we're dividing by a negative, so the less than or equal to switches direction. We left with 5 is greater than or equal to b, or b is less than or equal to 5. All right, and that's it for our first objective about inequalities. We're changing gears here. We're looking back at equations now for the rest of the notes. There's 3 possibilities when you're solving an equation. You might have infinitely many solutions. And you can always tell there's infinitely many solutions if, as you're solving, the variables on both sides cancel out and you get both sides equal to each other. In other words, you'll get something like 5 equals 5 or 0 equals 0 or x equals x or whatever. If both sides equal each other, that's a true statement. Everything is always equal to itself, right? And it's a true statement regardless of the value of the variable. I'll show you what I mean here in example 1. So when we distribute, we should get this. There's no like terms to combine, so let's get all the terms with the variable on one side and all the constants on the other. I chose to add 12 to both sides. Uh-oh. When I do that, I get negative 4v equals negative 4v. And again, I could try to get all the variables on one side, so I could add 4v to both sides to cancel out the left side and get 0, but it actually cancels out both sides this time. We get 0 equals 0, and that's the true statement I'm talking about. 0 is always equal to 0. It's always true no matter what value we pick for v. And because of that, v can be whatever we want. V could be 0, v could be 1, v could be a million. No matter what v is, 0 is always equal to 0. So if you get something like this, you just say infinitely many solutions. All right, number 2. Try this one on your own, see if you can get a true statement. Okay. When we distribute and combine our like terms, we end up getting down to this part here. And if you're really, once you've practiced this and get pretty good at it, you could notice here that both sides are equal to each other. They're always going to be the same no matter what n is. So you could stop here and say infinitely many solutions. But if you keep going, that's still okay. We could subtract 3 from this side so that the constant's only on the other side. But it turns out the constant cancels from both. We could subtract 5n from both sides to get the variable on one side. But again, n is going to get canceled from both sides, and we'll get 0 equals 0 again. So infinitely many solutions. It's not always the case that we have infinite solutions. In fact, usually we'll just have one solution. We did a lot of these in the last video. You should be able to solve equations like this. So try these on your own. Pause the video and then come back and check your work. All right, there we go. Notice that when you solve these, you get the variable by itself and a number on the right. So v equals 0. That's just 0 is the only value for v that works. Or 5 is the only value for x that makes this equation true in number 4. We haven't seen any of these yet, though. There's also a possibility that there's no solution at all. And what will happen is the variables will still cancel out, but what you're left with is a false statement. So if both sides do not equal each other, you'll get something that's false. You might get something like 0 equals 2. That's not true, right? They're different numbers. So let's try number 5 together. Actually, here, I'll just show you the whole thing, but we'll talk about it. We can distribute to get negative 7p plus 35. And then there's no like terms, but we can try to get rid of the 7p here so that there's only a p on the right side, but the p's cancel on both sides. And 36 is definitely not equal to 35. This is our false statement that I was talking about. So this will never be true, no matter what value p is. So because of that, there's no solution for p. Try number 6 on your own, see what you get. Okay, again, the variables cancel out on both sides and you get a false statement. 4 equals negative 3, that's ridiculous, that's not true. So there's no solution for v. All right, last problem, we have a word problem here. Again, make sure you circle the question and underline the important information. I'd like you to try that on your own, that's why I blocked it out. And then check and see if we circled and underlined the same thing. All right, hopefully you underlined that Brett has a $30 online voucher, and we should underline that the cost of each book is $4. It's also important to know that there's a single shipping charge of $2. The question we're asked is, we're asked to find how many books can he afford. And then in this case, the word problem doesn't tell us a variable. It doesn't say X represents this or that. So we should think about what's not known. Well, that's exactly what the question's asking. How many books? So let's let let's X or B for books, whatever you want to do, let's let that be our variable. I wrote, let X represent the number of books Brett buys. And then what we're going to do is we'll set up an inequality because Brett has options. He could just buy 0 books, right? But maybe he could buy more than that. Maybe he could buy 1 or 2 or 3, but there's probably also a maximum number of books he can buy with his limited funds. He's only got $30. And the beauty of this is you do not have to just write the inequality right away. Hopefully, it makes sense that the money he spends, it has to be less than or equal to $30. He has $30, right? He could spend all of it. He could spend some of it. He could spend none of it. So this is a great start. This shows a lot of work and a lot of reasoning. If this was a test, this would give you a good amount of points. Not all the points, but now we need to take this phrase here and turn it into math symbols. So we know that the cost of each book is $4, but we also know there's a shipping charge of $2 no matter how many books he buys. So that's exactly what we'll write. I didn't even use my symbols yet. The money he spends is going to be how much the books cost plus how much shipping costs. I guess we'll assume there's no taxes for this one, just to make it a little bit convenient. All right, so the shipping is $2 no matter how many books. The cost of the books is going to be 4 times, well, how many books he buys, right? If he buys 1 book, it'll be $4. If he buys 2 books, it would be 4 times 2, it would be $8, right? And so on. All of the hard word problem work is done now. This looks just like a different inequality from earlier in this video. Please solve this on your own for X and see what you get. Hopefully, you got X is less than or equal to 7. But for every word problem, you should always answer the question in context. Remember, X is the number of books he buys. So our final answer should be something in words. Brett can afford up to 7 books without spending more than his voucher. That's it for these notes. Ask a question, and I'll see you all in class.